Hello everybody, welcome to this video in which we're going to be talking about the transshipment problem. We talked about the transportation problem in the last video. The transshipment model is an extension of the transportation model. It is used when you have intermediate locations between supply and demand locations. So goods don't flow directly from supply to demand locations, they go through intermediate transshipment locations. Now the objective is similar. You still have to find the lowest cost way of transporting your goods from supply locations to demand locations through the transshipment locations. And we will assume that all the supply locations have known supply SIs and demand locations have known demand DJ, right? Now, cost will be represented as C AB, just as before. And this is what a transshipment network looks like. I'm sorry, there's slightly, there you go, right? So you have supply locations, you have demand locations, two supply locations S1 and S2, two demand locations D1 and DD. D1, let's say D6 and D7, just to be consistent, right? And then you have transshipment locations 3, 4, and 5. And so materials will flow from supply location to transshipment location and from transshipment location to demand location. And the idea is to figure out which supply locations supply which transshipment locations, and then which transshipment locations then send the supply over to which demand locations. Now the important factor to remember here is that none of the transshipment locations will end up with any inventory. Anything that you transport from supply to transshipment has to go to one of the demand locations. If you don't need supply at the demand locations, there is no point transporting them to the transshipment locations because you're paying cost for something that it's not needed at the demand location. So it's not necessary, right? So this is slightly more complicated than what you had before. So when you have these, when you have your objective function, instead of just j decision variables, we'll have xi to k, then xk to j, where k will be the intermediate locations, I will be the supply locations, and j will be the demand locations, right? And then because if total supply is less than total demand, that's the assumption that we're going to make, then all the supply going out of the supply locations is less than SI, all the demand going out of the, all the demand supply coming into the demand location is equal to DJ. So the supply and demand constraints are similar, but you'll also have another set of constraints called the transshipment constraints, where all the supply coming into a transshipment location should be equal to all the supply going out of a transshipment location. So what does this mean? Practically, what does that mean? So what it means is that for each of these nodes, you'll notice that there is supply going out and there is supply coming in. For the supply locations, the supply coming in is the supply that's available, and supply going out is all the supply that goes out to the transshipment location. And what you're saying with the supply constraint is that the sum of everything that goes out of the supply location, so x13, x14, and x15, the sum of all of that material that is transported has to be less than or equal to the supply that's available, right? So that's the supply constraint. For the demand constraint, again, there is supply going out, which is demand, and you have supply coming in, which is from the transshipment location. So you're saying that everything coming in should be equal to everything going out, because again, we are assuming that total supply is more than total demand. If it's the other way around, then demand constraints will be less than or equal to, and supply constraints will be equal to. So how do we write this constraint? We say x36 plus x46 plus x56, all the supply coming into node 6 should be equal to the demand. Similarly, for the transshipment locations, all the supply coming in should be equal to all the supply going out. So for node 3, it will be x13 plus x23, that's all the supply coming in, should be equal to x36 plus x37, that's all the supply going out. So everything coming in should be equal to everything going out. That way, the transshipment locations are balanced. You cannot have inventory left over at the transshipment locations, right? So you have supply constraints, you have demand constraints, and you have transshipment constraints, right? So here is another example. Okay. So New London, Providence locations of B&D Inc. supply 3 clients: Tom, Richard, and Harold. Tom Inc., Richard's Enterprises, and Harold and Son with these widgets. So B&D is Bennett and Daughter. So Bennett and Daughter buys these widgets from 2 manufacturers, manufacturer A, manufacturer B. And both of these manufacturers have a capacity of 75 each. So 75 here and 75 here. Now, currently, weekly demand by the users are 50 for Tom, 60 for Richard, and 40 for Harold, right? 50 here, 60 here, 40 here, right? And then, because of long-standing contracts on past orders, unit transportation costs for manufacturers. So these are the transportation costs from the manufacturers to B&D's locations, and from B&D's locations to their customers. These are the transportation costs, right? So with this, we need to set up a so we need to figure out how many of the 75 unit capacity gets transported to London and Providence, how many of the 75 unit capacity from B gets transported to London and Providence, and from New London and Providence, and then from New London and Providence, how many units are you sending to Tom, how many are you sending to Richard, how many you're sending to Harold, and so on. So that's basically the problem here. So let's set this up. So again, I'm gonna use the same Excel file. We have the transportation model. Let's do the transshipment model here. Right? I'm gonna copy this first. This is the first part of the supply chain. So the first part of the supply chain goes there. And then we'll do the second part of the supply chain, which is right there. And I'm gonna do that there, put it over there. Okay. Just gonna fix a few things quickly. Okay. And we make the font bigger. There you go. So the first part of the supply chain right there. That's the second part of the supply chain. We have more data. So A and B manufacturing facilities, they both have capacities 75 and 75, right? So total capacity is 150. Remember that. And demand for Tom, Richard, and Harold. We know the 3 demand values. That is 50, 60, and 40. Right? Okay. A few things I want to know. First things first. Total capacity is 150. So you can, when you're buying widgets from both manufacturing facilities A and B from your supplier, you can acquire a maximum of 150 widgets. But demand is 200. So total demand is 200, which means that you will not be able to satisfy all demand. You can only satisfy part of the demand. And that's also part of what we figure out, how many units of demand get satisfied. So in this case, so supply will be fully used up, but demand will not be fully satisfied. So supply constraints will be equal to constraints, and demand constraints will be less than or equal to constraints. Now, transshipment constraints will always be equal to, because all supply coming in has to go out, so that will always be equal to. Let's begin with the objective first. Oh, we need to set up spaces for our decision variables first. I need to do that. So this is the first part of the supply chain, and this, oh, I don't need this. Sorry about that. Okay, this is the second part of the supply chain. So these will tell you how many units get transported from manufacturing facilities A and B to New London and Providence, and these 6 cells will tell you how many units are transported from New London and Providence to each of your 3 customers, right? So let's write the objective first. So again, you're going to multiply corresponding numbers with corresponding numbers. You're going to add them up. So I will use the sum product formula, but here you will need 2 separate sum product formulas. So the sum product formula first for the first part of the supply chain, where you take the first part of the supply chain, comma, the decision variables for the first part of the supply chain, plus sum product, the second part of the supply chain, comma, decision variables for the second part of the supply chain. Now remember, capacity and demand values don't go into this formula. This is just the cost times the number of units, cost times the number of units. That is all that goes into the objective function, right? This is demand. Okay. Now, your objective function is here. Now let's write the constraints. First, let's begin with the supply constraints. That right the first time. Supply constraints. So we have 2 locations, amount supplied, and this is the capacity. Okay, so amount supplied out of manufacturing facility A. This is the total amount supplied. So everything coming from A to New London plus everything coming from A to Providence, right? And this has to be equal to, in this time, the capacity. So again, with this, I can just copy the formula down. So this is all the supply coming out of manufacturing facility B, and that has to be equal to 75. Now let's write the demand, let's write the transshipment constraints next. So let's write demand constraints. Do it in the same order. For Tom, Rich, and Harold. So this is the amount supplied, and this is the demand. Nope, not the constraint. Okay, so demand we know, so demand values are here. Amount that is supplied to Tom is all the supply coming in from New London and Providence going into Tom, going to Tom Inc. Right. There you go. Right. So everything coming into Richard's company and everything coming into Harold's company. And then you have 50, 60, and 40 in the demand values. So remember, total demand is more than total supply. So demand constraints will be less than or equal to constraints. Supply constraints will be equal to constraints. Finally, transshipment. So transshipment constraints for New London and Providence. I'm going to call it coming in, going out. So all the supply coming in and all the supply going out should be equal to each other. The sum of all the supply coming in to New London, all the supply coming into London from the 2 manufacturing facilities should be equal to all the supply going out of New London to Tom, Richard, and Harold, right? Same for Providence, all the supply coming in. You cannot copy the formulas down here, they won't work. All the supply coming into Providence should be equal to all the supply going out of Providence. And there you go. So supply coming in, supply going out. So we have all the constraints set up, right? So let's put it into solver. Data solver, right? The objective is right here. That's the objective where we wrote the two sum product formulas, and it is still cost minimization, right? Now changing variables, this is where you have to be careful now. Let me just quickly change that to LP linear. So changing variables, so I'm going to click on that. So this is the first set of variables, and then you have to put a comma. Don't forget the comma, otherwise you'll just overwrite it. And then the next 6 variables, right? So you got four variables here and then 6 variables here. Now let's write the constraints. First, the supply constraint. So total supply has to be equal. So remember, this is supply constraints are equal to, because total supply is less than total demand. Okay, so I'm going to click on add this time. So total demand, so this is all the demand values. So this has to be less than or equal to what the actual demand values are, because you cannot satisfy all demand. Click on add. Finally, total supply coming in has to be equal to total supply going out of the transshipment locations. Now I'm going to click OK because I don't have any more constraints. And there you go. So that's my objective. So 4 decision variables here and then 6 decision variables here. Cost minimization. So don't forget to check the minimum. Then you have 3 sets of constraints, right? So this is the transshipment constraints. These are the demand constraints, and these are the supply constraints. So supply is less than or equal to demand is equal to, because total demand is more than total supply. If it's flipped around, then total demand, if total demand is less than total supply, then demand constraints will be equal to, supply constraints will be less than or equal to. With that, I'm going to click on solve. And there you go. So this is your supply chain. So supply chain says that everything coming in from manufacturer A, manufacturing facility A, should go to New London, nothing to Providence. Everything coming from B should go, none of it should go to New London, everything should go to Providence, right? You are using up all the capacity. Now, let's look at wait a second, 50, 60, 40. I'm so sorry. That doesn't add up to 200. That adds up to 150. Couldn't math, right? No wonder everything got messed up here. So when you put it into solver, because one set of these constraints was equal to, the other set being less than or equal to did not matter. But technically, you should put all your constraints as equal to constraints in this case. But that's fine. Okay. Now, so you're sending 75 units to New London. Of that, 50 units go to Tom, 25 to Richard. You're sending 75 to Providence. From Providence, nothing goes to Tom, 35 goes to Richard, and 40 goes to Harold, right? And all of this, the total cost of doing all of this, $1,035, and you cannot do it for less than $1,035, right? And that's the network. Okay, so this is how you do a transshipment model. And that's it for this video. If you have any questions, again, please feel free to email me, and I'll see you all in a different video. All right, take care.